This is SpaceTime Series 25, Episode 133. Coming up on SpaceTime, the mysteriously bright flash pointing directly at the Earth. Construction finally begins on the world's largest telescope, the Square Kilometre Array, and the Mars Ingenuity helicopter returns to flight status. All that and more coming up on SpaceTime.
Welcome to Space-Time with Stuart Gary.
Earlier this year, astronomers detected an extraordinarily bright flash in a part of the sky halfway across the universe where no such light had ever been observed before. From rough calculations, they quickly worked out this flash appeared to give off more light than 1,000 trillion suns. Now, a report in the journal Nature Astronomy has concluded that this flash marked the death throes of a star being literally torn apart and consumed by a supermassive black hole. The flash was first detected by the Zwicky Transient Facility All-Sky Survey, based at the Mount Palomar Observatory in California. The sighting was quickly posted on an astronomy website, where the signal drew the attention of astronomers from around the world. Over the next few days, multiple telescopes focused on the signal in order to get more and more data across multiple wavelengths, looking in the X-ray, ultraviolet, optical and radio bands to see what could possibly be causing such an enormous amount of light. The flash, now named Eta 2022 CMC, was identified as most likely being a relativistic jet of matter and energy streaking out from a supermassive black hole close to the speed of light. The material is what's left of a star that moved too close to the black hole and was torn apart by a gravitational tidal disruption event, releasing a huge amount of energy in the process. Now, astronomers have observed other such tidal disruption events before, but Eta 2022 CMC is much brighter than any previous such event ever discovered. Its spectra indicates a hot source around 30,000 degrees, which is typical for a tidal disruption event. The source is also the most distant tidal disruption event ever detected, some 8.5 billion light-years away. That's more than halfway across the universe. The team were able to measure the distance to Eta 2022 CMC using the European Southern Observatory's Very Large Telescope in Chile. But there begs the question, how could such a distant event appear so bright in our skies? Now, the astronomers eventually concluded it's because the black hole's jet is pointing directly towards the Earth, making the signal appear brighter than what the jet would were it pointed in any other direction. The effect is called Doppler boosting, and it's similar to the amped-up sound of a passing siren. Eta 2022 CMC is the fourth Doppler-boosted tidal disruption event ever detected, and it's the first such event that's been observed since 2011. It's also the first tidal disruption event observed using an optical sky survey. Still, as more powerful telescopes start up in coming years, they'll reveal more tidal disruption events, which in turn will shed more light on how supermassive black holes grow and shape the galaxies around them. One of the study's authors, Matteo Lucchini from MIT, the Massachusetts Institute of Technology, says scientists are pretty sure there's a supermassive black hole at the heart of most, if not all, galaxies, and that these formed very quickly in the early years of the universe. That tells astronomers that they feed very quickly, though it's not known exactly how that feeding process works. So sources like this will help provide new clues. Following Eta 2022 CMC's initial discovery, the authors focused on the signal using the Neutron Star Interior Composition Explorer, or NISA X-ray telescope, mounted aboard the International Space Station. Things initially looked fairly normal for the first 3 days, but then the source became really bright. Typically, such bright flashes in the skies are gamma-ray bursts, extreme jets of X-ray emissions that spew out from the collapse of massive stars during supernova explosions, marking the ends of their lives. But this particular event was 100 times more powerful than the most powerful gamma-ray burst afterglow. So the teams gathered observations from other X-ray, radio, optical and ultraviolet telescopes, and they tracked the signal's activity over the following few weeks. The most remarkable property they observed was the signal's continued extreme luminosity in the X-ray band. They found that X-ray emissions from Eta 2022 CMC swung widely by a factor of about 500 over just a few weeks. They suspect that such extreme X-ray activity must be being powered by an extreme accretion episode. In other words, there are huge chunks of this shredded star falling onto the accretion disk around the black hole and being consumed. Most of this material will eventually pass beyond the event horizon, a sort of point of no return, beyond which matter falls forever into the black hole singularity. But some of it, so-called breadcrumbs, gets caught up in powerful magnetic field lines and is directed out as jets travelling at close to the speed of light perpendicular to the black hole's accretion disk. And it was one of these events which just happened to generate jets of matter pointing directly at the Earth. The scientists were literally looking down the throat of a quasar. Now, if AT 2022 CMC's luminosity is the result of a Earth-targeting jet, well, that begs the question, how fast must this jet be moving to generate such a bright signal? To determine that answer, Lucchini modelled the signal's data, assuming the event involved the jet heading directly at Earth. It turns out this jet would be travelling at 99.99% the speed of light. To produce such an intense jet, the black hole must be in an extremely active phase, what the study's authors are describing as a hyper-feeding frenzy. In fact, they speculate this black hole must be swallowing around half a sun's worth of stellar material every Earth year. This is SpaceTime. Still to come, construction finally underway on the world's largest telescope, the Square Kilometre Array. And it's been grounded for a while, but the Mars Ingenuity helicopter has returned to flight status. All that and more still to come on SpaceTime. Well, we've been talking about it for well over a dozen years now, and planning for it's gone almost as long. Now, finally, construction of the world's largest telescope, the Square Kilometre Array, is finally getting underway, with ceremonies at the future telescope sites in Western Australia and South Africa. Over 1,000 engineers and scientists have been involved in designing the Square Kilometre Array radio telescope over the past decade. To give you an idea of the scale of this monster, it covers 2 continents, Australia and South Africa. More than 100,000 antennas and dozens of dishes are being set up in the Australian site, located in outback Western Australia. And almost 200 more dishes are being built at the South African site. In simple terms, this makes the Square Kilometre Array the biggest single scientific facility on Earth, and one that will provide unparalleled views of the universe. There are 7 founding nations for the SKA or Square Kilometre Array project. They include Australia, the United Kingdom, South Africa, China, Italy, the Netherlands and Portugal. And several other nations, including India, Sweden, Canada, France, Malta, New Zealand, South Korea, Spain and Switzerland, are also interested in joining the project at some stage. Headquarters will be at the Jodrell Bank Observatory in the north of England, and the project will use 2 of the world's largest supercomputers, one based at Perth, the other in South Africa. The observatory's size and wide range of operating frequencies will make the facility at least 50 times more sensitive than any other radio instrument in the world. There will be the SKA low-frequency phased arrays of Doppler antennas covering the 50 to 350 MHz frequency range and grouped in 100-metre diameter stations, each containing about 90 elements. The SKA mid-frequency array will include several thousand 12-metre dish antennas, and they'll cover the 350 MHz to 14 GHz frequency range. Then there's the SKA survey array. It'll use a compact array of 12 15-metre diameter parabolic medium-frequency dishes, each equipped with a multi-beam phased array feed with a large field of viewing covering the 350 MHz to 4 GHz range. The antennas will be sucking in so much data, it'll need to be processed and evaluated before it's even sent to the computers for storage and then distribution to scientists. This will all need to be done automatically using new artificial intelligence programs. Some 600 petabytes of data is expected to be stored and distributed worldwide to the science community every year. That's enough to fill more than 500,000 top-end laptops. The Australian facility will be based at the CSIRO's Murchison Radio Astronomy Observatory in outback Western Australia. Now, this observatory already has 2 operational main instruments. The Australian Square Kilometre Array Pathfinder, or ASCAP, which uses 36 identical 12-metre dishes which can work together as a single instrument, providing fast survey speed and high sensitivity. and the Murchison Wide Field Array, consisting of 80 300 MHz low-frequency, fully cross-correlating signal dipoles on 128 phase tiles, each comprising 16 dipoles. A third separate instrument is the experiment to detect the global EOR signature or edges antenna and low-noise amplifier radio telescope. It's designed to detect the redshifted 21-centimetre hydrogen line from the cosmic dawn, the epoch of reionization, which corresponds to a redshift of 27. The South African precursor facility is the Meerkat array of 64 13.5-metre dishes covering the 580 MHz to 14 GHz frequency range, plus the 7-dish Cat7 engineering and science testbed instrument. No matter what scale you view this on, the SKA project is enormous.
Humans have always been drawn to the mysteries of the night sky. On clear nights we can see thousands of stars and galaxies with our naked eyes alone. Optical telescopes have allowed us to see millions more and taught us much of what we know about the universe by collecting the light that finds its way to Earth from space. More recently, radio telescopes have enabled us to gather radio waves from space, providing a view of a universe filled with gas and exotic physical processes in more detail than ever before. Modern technology is now driving a rapid expansion of the capability of radio telescopes, and with it, their potential for new and exciting discoveries. For decades, scientists and engineers from all over the world have been developing a radio telescope so large and powerful that it will be able to see almost all the way back to the beginning of the universe. This telescope is known as the Square Kilometre Array, or SKA, a project so ambitious that it will skip a generation in the development of radio telescopes. The SKA will be constructed in two places, Southern Africa and Australia, and will be made up of millions of antennas of different types, linked together by fibre optic networks and feeding data into huge supercomputers. Australia's SKA site at the Murchison Radio Astronomy Observatory in Outback, Western Australia, will be home to a low-frequency array of millions of chest-high dipole antennas, which will be spread out in clusters over an area up to 100 kilometres in diameter. The low-frequency array, or SKA Low, will collect radio waves from the farthest reaches of space that have stretched out and shifted from high to lower frequency waves as the universe has expanded. Phase 1 will see over 100,000 of these antennas placed in the Australian outback, extending into the millions over the following decade. When fully operational, the array will generate staggering quantities of data, several times more, in fact, than today's entire global internet traffic. This data will help us provide answers to some of humanity's oldest and most profound questions about the universe around us. All of the data gathered by the SKA in Australia will be correlated and packaged up on-site before travelling via a dedicated high-capacity fibre optic connection to the coastal city of Geraldton and then on to Perth, over 700 kilometres away. In Perth, the data will be processed at the Pawsey Supercomputing Centre, an innovative and purpose-built supercomputer facility. The sheer volume of data generated by the SKA will require a supercomputer faster and more powerful than any currently in existence. Though construction of Phase 1 of the SKA project is not due to begin until the latter half of this decade, the Australian core site is already home to two SKA precursor telescopes. Testing and developing technology for the SKA, these are both state-of-the-art radio telescopes in their own right. The Australian SKA Pathfinder Telescope, or ASCAP, built by Australia's CSIRO, is a 36-dish survey array that can capture images from an area of the sky 30 times larger than previous radio receivers, thanks to its revolutionary phased array feed receiver technology, a feature which helps it to survey large areas of the sky quickly and accurately. The Murchison Wide Field Array, or MWA telescope, a collaboration between several international universities and organisations, is designed to pick up low-frequency radio waves from deep space. It is already doing groundbreaking science, and the lessons being learned in its design and construction will help to inform the design of the SKA low-frequency array. Both the ASCAP and the MWA are on the brink of making discoveries and breaking records in radio astronomy. Both are already playing important roles in the development of the world's largest telescope, the SKA. And Australia, as proud co-host of the SKA, looks forward to playing a key role in its development, helping to unlock the secrets of the universe.
This is SpaceTime. Still to come. It's been granted for a while, but the Mars Ingenuity helicopter has now returned to flight status. And the December solstice, the ticking time bomb that is Eta Carinae, and the rock comet Phaethon are among the highlights of the December night skies on Skywatch. NASA's Mars Ingenuity helicopter has successfully performed a short test flight following a major software update. The massive reprogramming will allow the little rotocopter to land more safely and navigate over more rugged terrain. The brief 18-second test flight saw the 1.8 kilogram tissue box-sized helicopter briefly hover after takeoff above the Martian surface before landing again just 5 meters away. It was Ingenuity's first flight since September 29th, and the 34th since arriving on Mars, attached to the belly of the Perseverance rover back in February last year. Ingenuity was only ever meant to be a technology demonstrator, undertaking just a handful of flights in order to prove that it was possible to fly over the surface of another planet. But it's proven to be an extremely useful and reliable scout, finding interesting rock outcrops and better ways for the Perseverance rover to get there. However, the change in seasons has meant the Martian atmosphere is getting even thinner, forcing Ingenuity's rotors to work even harder. And with the mission now moving focus from the broad expanse of the Jezero crater floor to the more rugged terrain of the river delta region, the new software will allow Ingenuity's downward-facing camera to detect risky objects before landing and steer the rotocopter to avoid them. The software also makes Ingenuity more confident in flight. The helicopter was originally programmed to fly over flatlands, and its cameras were getting confused by the hilly landscapes, interpreting it as the helicopter veering off course, and this resulted in the helicopter really flying off course in a misguided attempt to stabilize its flight path. The new software update corrects this flat ground assumption by using digital elevation maps of Jezero crater to help navigation software distinguish between changes in terrain and vehicle movement. The new software upgrades will allow Ingenuity to scout a wider range of terrain types for Perseverance to explore in detail. This is SpaceTime. Time now to turn our eyes to the skies and check out the night skies of December on Skywatch. December is the 12th and final month of the year in both the Julian and Gregorian calendars. Its name comes from the Latin word decim, meaning 10, because it was originally the 10th month of the year in the old Roman calendar, which began in March. The astronomical highlight of the month is the December solstice, which this year occurs at 8:48 a.m. Australian Eastern Daylight Time on the morning of Wednesday, December the 21st. That's 4:48 p.m. Wednesday afternoon, December 21st, US Eastern Standard Time, and 21:48 in the evening, Greenwich Mean Time. The December solstice is when the sun appears to reach zenith directly over the Tropic of Capricorn. In the United States and most of the Northern Hemisphere, it marks the winter solstice, signifying the first day of winter. But the good news is that from now on the days start to get longer again. South of the equator, summer has well and truly arrived, and the days are usually at their warmest. The seasons occur because of a tilt in Earth's spin axis, which is inclined at 23.4 degrees in relation to the Sun. Now, generally speaking, Earth's axis always appears to point at the same position in space, regardless of the position of the Earth in its orbit around the Sun. So on the day of the December solstice, Earth's south pole is tilted directly towards the Sun, so the southern hemisphere gets more daylight and consequently more direct sunlight, so it's hotter and it's the southern hemisphere summer. 6 months later, during the June solstice, the northern hemisphere is tilted towards the sun, and so it's the northern hemisphere which experiences summer, while the southern hemisphere gets less daylight, longer nights, and the sunlight strikes the surface at a shallower angle, meaning less heat, and consequently it's the southern hemisphere's winter. In between these, we have the March and September equinoxes. That's when the northern and southern hemispheres get roughly equal amounts of daylight and heat, in the process giving us the seasons of spring and autumn. Now earlier we said that generally speaking, Earth's axis always points to the same position in space regardless of Earth's orbital position around the Sun. And while that's true in our day-to-day lives, over geologic time, a gravity-induced effect known as axial precession causes a slow and continuous change in the orientation of Earth's rotational axis. You can see the same effect in the precession of a spinning top as the axis traces out a pair of cones joined at their apses. Earth's precession is known as the precession of the equinoxes. That's because the equinoxes move westwards along the ecliptic relative to the fixed background stars. This slow precession means that over 25,772 years, the positions of the north and south celestial poles appear to move in circles against the space-fixed backdrop of stars. So, while today the star Polaris lies approximately at the North Celestial Pole, this will change over time, with Gamma Cephei becoming the North Star in about 3,200 years. It also means the seasons would slowly move into different calendar months. But of course we make adjustments for this in the calendar to compensate. In most parts of the world, the seasons begin on the day of the solstice or equinox. However, Australia follows meteorological seasons, which begin on the first day of a particular calendar month. The 1st of March for autumn, the 1st of June for winter, September the 1st for spring, and the 1st of December for summer. Because of the relatively small amount of elongation in Earth's orbit around the Sun, Earth's seasons are determined by its axial tilt rather than its orbital distance from the Sun. Now currently, Earth's closest orbital position to the Sun, perihelion, occurs about 2 weeks after the December solstice, and it's furthest from the Sun at aphelion about 2 weeks after the June solstice. That means the next perihelion will occur on Thursday, January the 5th at 3:17 a.m. Australian Eastern Daylight Time, when the Earth will be just 147,098,925 kilometres from the Sun. That's 11:17 in the morning of Wednesday, January the 4th, US Eastern Standard Time, and 16:17 in the afternoon of January the 4th, Greenwich Mean Time. Like axial precession, the Earth's orbit also changes gradually over geologic timescales, getting more or less elongated and changing perihelion and aphelion. Even the degree of tilt of the Earth's spin axis changes over thousands of years. Now collectively, these are all known as Milankovitch cycles, after the Serbian geophysicist and astronomer Milutin Milankovitch, who in the 1920s hypothesized that variations in eccentricity, axial tilt and precession resulted in cyclical variations in solar radiation reaching the Earth, and that this strongly influenced Earth's climatic patterns. Okay, let's start our tour of the night skies in the west, where midway up from the horizon you'll find Fomalhaut, the brightest star in the constellation Pisces Austrinus, the southern fish. Fomalhaut is a young white spectrotype A main sequence star, about 1.8 times the diameter of the Sun, located about 25 light-years away. A light-year is about 10 trillion kilometres. The distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Main sequence stars are those undergoing hydrogen fusion into helium in their core. Astronomers describe stars in terms of spectral types, classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive stars known are spectral type M red stars. Each spectral classification is also subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and a Roman numeral to represent luminosity. Now put all that together and our Sun is officially classified as a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are about 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. In 2008, astronomers detected planets orbiting around Fomalhaut. It's not known if anyone was looking back. 5,000 years ago, the ancient Mesopotamians used Fomalhaut to mark the northern hemisphere's winter solstice. Turning to the left of Fomalhaut, you'll find the star Achernar Alpha Eridani, the brightest star in the constellation of Eridanus the River. Located 139 light-years away, Achernar has about 7 times the diameter of the Sun and rotates some 15 times faster, giving it an oblate shape. The effect of this rapid rotation is that the star flattens at the top and bottom, but bulges in the middle. In fact, its equatorial diameter is around 50% greater than its polar diameter. Achernar is actually a pair of multiple star systems, Alpha Eridani A and Alpha Eridani B. The primary star, Alpha Eridani A, is a hot blue spectral type B main sequence star. Its smaller companion, Alpha Eridani B, is a spectral type A white star. The pair orbit each other at a distance of about 12 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres or 8.3 light minutes. Moving further left from Achernar, and just above the horizon this time of year, is Canopus, the brightest star in the southern constellation of Carina the Keel and the second brightest star in the night sky after Sirius. Canopus is a white giant, nearing the end of its life and located about 310 light-years away. It has about 8.5 times the mass of the Sun, but has now expanded out to about 71 times the Sun's diameter. Canopus is hard to miss. It has some 1,300 times the brightness of the Sun and is in fact the brightest star within 700 light-years of Earth. Its name originates in mythology from the time of the Trojan Wars and the navigator for Menelaus, king of Sparta. Located between Canopus and the Southern Cross in Carina, in the Trumpler-16 open star cluster, is the ticking time bomb known as Eta Carinae. Eta Carinae is a pair of huge blue stars undergoing the violent final phase of their existence before exploding in massive core collapse supernovae. The binary system, located some 8,500 light-years away, is buried deep inside the giant nebula of Carinae, a massive cloud of gas and dust between 6.5 and 10,000 light-years away. The stars in Eta Carinae are both classified as highly luminous spectral type O blue hypergiants. Its primary star is huge, estimated to be between 150 and 250 times the mass of our Sun, with around 5 million times the Sun's luminosity, 800 times its radius, and a surface temperature of some 32,500 Kelvin. This is the only star known to produce ultraviolet laser emissions. And astronomers estimate it's already lost some 30 times our Sun's mass. The companion star, although smaller than the primary, at just 30 to 80 solar masses, 20 times the Sun's radius, is even hotter, with a surface temperature of around 37,200 Kelvin. The two stars orbit each other every 5.54 Earth years, cocooned in a thick twin-lobe cloud of gas and dust known as the Homunculus Nebula, a spectacular bipolar emission and reflection nebulae. The nebula was created when Eta Carinae underwent a spectacular eruption starting in 1837. Known as the Great Eruption, it eventually reached its peak in 1843, by which time it was one of the brightest objects in the night sky, almost as bright as Sirius, before gradually fading away again by 1856. Eta Carinae underwent another significant but smaller eruption in 1892, and it's again been getting steadily brighter since 1940. Both Eta Carinae and its surrounding shroud of dust generate huge amounts of infrared radiation, making it the brightest infrared source in the sky. Both stars are nearing the end of their lives on the main sequence and are expected to go supernova in an astronomically short space of time. When it does so, Eta Carinae will be easily visible in daylight and may even become brighter than the full moon for months on end. No one knows exactly when Eta Carinae will go supernova. It could be tonight, or it could be in 1,000,000 years from now. A single star, originally around 150 times as massive as the Sun, would typically reach core collapse as a Wolf-Rayet star within, say, 2 to 3 million years. At low metallicity, many massive stars would collapse directly to form a black hole, with no visible explosion at all, or a subluminous supernova at most. And a small fraction will produce what's known as a pair instability supernova. But at solar metallicity and above, there's expected to be enough mass loss before collapse to allow a visible supernova to occur. By the way, that term metallicity, well, astronomers regard all elements on their periodic table to be metals other than the hydrogen and helium created in the Big Bang 13.82 billion years ago. Highly massive progenitor stars could also eject sufficient nickel to cause a superluminous supernova simply from radioactive decay. And the resulting remnant would be a black hole, since it's highly unlikely that such a massive star could ever lose sufficient mass for its core not to exceed the limits of a neutron star, somewhere around 2.2 to 2.4 times the mass of the Sun. But the existence of a massive companion star in Eta Carinae brings many other possibilities into consideration. For example, if Eta Carinae A was rapidly stripped of its outer layers, it might become a less massive WC or WO type star when core collapse was reached. And this would result in a Type 1b or Type 1c supernova due to the lack of hydrogen and possibly helium. And these supernovae are thought to be a possible originator for some types of gamma-ray bursts, generally regarded as the most powerful explosions in the universe since the Big Bang. Several unusual supernovae and imposters have been compared to Eta Carinae as possible examples of this fate. One of the most compelling is SN2009 IP, a blue supergiant which underwent a supernova imposter event in 2009, with similarities to Eta Carinae's Great Eruption. Then an even brighter outburst occurred in 2012, which is likely to have been that star's true supernova. Still, the most likely theory for Eta Carinae's ultimate fate would be collapsing to form a stellar mass black hole, with the energy released as jets along the axis of rotation as gamma-ray bursts. A typical core collapse supernova at the distance of Eta Carinae would look every bit as bright as Venus in the sky. And remember, only the Sun and Moon are brighter. A superluminous supernova could be 5 magnitudes brighter, potentially the brightest supernova in recorded history. The good news is Eta Carinae is not expected to produce a gamma-ray burst, and its axis isn't currently aimed anywhere near the Earth. At 7,500 light-years from the star, it's unlikely to directly affect terrestrial life on Earth when it does blow, thanks primarily to our planet's atmosphere and magnetosphere. But the ozone layer could be damaged, as with any orbiting spacecraft and astronauts in space at the time. And at least one paper has projected that complete loss of the Earth's ozone layer is a plausible consequence of a supernova, which would result in a significant increase in ultraviolet radiation reaching the Earth's surface from the Sun. But this would require a typical supernova to be closer than 50 light-years from Earth, and even a potential hypernova would still need to be closer than Eta Carinae. Another analysis of possible impact discusses more subtle effects from the unusual illumination, such as possible melatonin suppression, with resulting insomnia and an increased risk of both cancer and depression. Okay, enough gloom and doom for now. Let's turn to the east, and looking just above the horizon is the star that outshines Canopus to take the title of the brightest star in our night sky, Sirius the Dog Star. And next to it, in the east-northeastern skies, just above the horizon, is the constellation of Orion the Hunter. Now, if you look closely, you'll see a very bright red star. That's the supergiant Betelgeuse, better known to most people these days as Betelgeuse. Don't say it 3 times. In ancient times, before centuries of mispronunciation, the name started out as Isbet al-Yauza. Betelgeuse is one of the largest and most luminous stars visible to the unaided eye. Located some 430 light-years away, this bloated old red supergiant is nearing the end of its life. And it's truly massive. Some 1,100 times the diameter and 100,000 times the brightness of our Sun. Like Eta Carinae, Betelgeuse is destined to explode as a core collapse supernova sometime in the near future. Betelgeuse marks the right shoulder of Orion the Hunter, although it's all upside down from the perspective of anyone in the southern hemisphere, as Orion was a hunter in Greek mythology, so the constellation was viewed from the northern hemisphere. The earliest depiction that has been linked to the constellation of Orion is a prehistoric mammoth ivory carving found in a cave in the Acht Valley in West Germany in 1979. Archaeologists have estimated that it was fashioned sometime between 32 and 38,000 years ago. The distinctive pattern of Orion has been recognized in numerous cultures around the world, including the ancient Babylonian star catalogues dating to the late Bronze Age. In Greek mythology, Orion was a gigantic, supernaturally strong hunter of ancient times. He was the son of a Gorgon and Poseidon, also known as Neptune, the god of the sea in the Greco-Roman tradition. One day, the goddess Gaia became enraged at Orion after he boasted that he would kill every animal on Earth. So she sent a scorpion to sting Orion to death. However, Ophiuchus the serpent-bearer revived Orion with an antidote. This is given to be the reason that the constellation Scorpius chases Orion across the sky, with the constellation Ophiuchus standing midway between them. The other major stars in Orion include Rigel, Orion's left foot. It's a blue supergiant. Having exhausted its core hydrogen, Rigel's now swollen out to between 79 and 115 times the Sun's radius, and it's fusing heavy elements in its core, meaning it too will soon likely go supernova, eventually collapsing to form a neutron star. Rigel's estimated to be somewhere between 120,000 and 279,000 times as luminous as the Sun. And it's a binary system located 860 light-years away. Its companion star, Rigel B, is some 500 times fainter than the supergiant Rigel A, and it's only visible through a telescope. But Rigel B itself is a spectroscopic binary system comprising of two main sequence blue-white stars. Spectroscopic binaries are double star systems orbiting each other in such a way that they can only be visually separated from our vantage point here on Earth by their different spectroscopic signatures. The two stars making up Rigel B are estimated to be 3.9 and 2.9 times the mass of our Sun, respectively. And one of these stars, Rigel BB, may itself be a binary. And Rigel B also appears to have a very close visual companion, Rigel C, of almost identical appearance. The third brightest star in Orion is Bellatrix, Orion's left shoulder. It's a spectrotype B main sequence blue star with about 8.6 times the mass and 6 times the radius of the Sun. Bellatrix is located some 250 light-years away. It's estimated to be about 25 million years old. That's enough for a star of this mass to have consumed most of the hydrogen in its core and begin to evolve away from the main sequence into a blue giant. Now, if you look at the three stars which make up Orion's belt, you'll see another three stars which make up Orion's sword hanging from the belt. If you look carefully at the middle star, you'll notice it's a bit fuzzy looking. That's because it's not a star, it's the Great Nebula of Orion, Messier 42. Located just 1,344 light-years away, M42 is the nearest massive star-forming region to Earth. The M42 nebula is estimated to be about 24 light-years across and has a mass of over 2,000 suns. The Orion Nebula is one of the most scrutinized and photographed objects in the night sky, and it's among the most intensely studied celestial features. In fact, the nebula has revealed much about the process of how stars and planetary systems are formed from collapsing molecular gas and dust clouds. By studying M42, astronomers have directly observed protoplanetary disks, brown dwarfs, tense and turbulent motions of gas, and the photoionizing effects of massive nearby stars in the nebula. The Orion Nebula contains a very young open star cluster known as the trapezium due to the asterism of its four primary stars. And the trapezium is a component of the much larger Orion Nebula cluster, an association of about 2,800 stars within a diameter of just 20 light-years. One of the most stunning nebulae in the constellation Orion is the spectacular Horsehead Nebula, Barnard 33. The Horsehead is a dark nebula located just south of the star Alnitak, which is the furthest east on Orion's belt, and is part of the much larger Orion Molecular Cloud complex. Located around 1,500 light-years away, the Horsehead Nebula was first recorded in 1888. It's one of the most identifiable nebulae because of the shape of its swirling cloud of dark dust and gases, which bears a remarkable resemblance to a horse's head when viewed from Earth. One of the astronomical highlights of December is the annual Geminids meteor shower, which usually peaks around December the 13th and 14th. Radiating out from the direction of Gemini, the Geminids are unusual in that they're not generated by a comet as most other meteor showers are, but are produced by the debris trail left behind by the asteroid 3200 Phaethon. This makes the Geminids, together with the Quadrantids, the only major meteor showers not originating from a comet. 3200 Phaethon is highly unusual. Its high orbital eccentricity more closely resembles that of a comet than an asteroid. And in fact, it may be an asteroid that's simply run out of the volatile gases that characterize a comet. Phaethon's orbit crosses all the inner terrestrial planets, Mercury, Venus, Earth and Mars. It'll make its closest approach to Earth on December the 14th, 2093, when it will pass just 2,960,000 kilometres from Earth. The 5-kilometre wide asteroid is classified as potentially hazardous. Interestingly, Phaeton's named after the son of the Greek sun god Helios. Legend has it that Phaethon almost destroyed the Earth by stealing Helios's chariot and scorching the Earth with the sun, almost causing the apocalypse. Phaethon approaches the Sun closer than any other named asteroid, with a perihelion of less than 21 million kilometres. That's less than half of Mercury's perihelion distance. Coming so close to the Sun causes its surface temperature to reach over 750 degrees Celsius, and observations by NASA's Stereo spacecraft have observed dust trails radiating off its surface. In fact, in 2010, Phaethon was seen ejecting dust. Now, scientists think the intense heat generated by its close approach to the Sun is causing fractures in gravel and rocks on the asteroid's surface, similar to mud cracks in a dry lake bed. Phaeton's composition also fits the notion of a cometary origin. It's classified as a B-type asteroid because it's composed of dark material. And B-type asteroids are thought to be primitive volatile rich remnants of the early solar system. Its composition, orbit and dust trail have all combined to lead astronomers to refer to Phaethon as a rock comet. The Geminids meteors it produces have a yellowish hue to them, and they tend to be a bit larger and more solid than typical meteors from comets. They also move more slowly, travelling at around 35 kilometres per second, compared to some cometary meteor showers which travel at speeds of up to 72 kilometres per second. And interestingly, the Geminids are thought to be intensifying every year, with recent showers seeing up to 160 meteors per hour under optimal conditions. In the Northern Hemisphere, expect to see up to around 120 meteors per hour between midnight and 4 a.m, but only from a dark sky. Now, well north of the equator, the radiant rises about sunset, reaching a usable elevation from local evening hours onwards. In the Southern Hemisphere, you won't see as many meteors, perhaps just 10 to 20 an hour. That's because the radiant doesn't rise above the horizon. Now, also for listeners in the Northern Hemisphere, there's a second meteor shower in December, the Ursiids, which radiate out from Ursa Minor, the Little Dipper. The Ursiids are generated by debris left behind by the comet 8P Tuttle. They're a compact stream, peaking on the night of December the 22nd and the early morning hours of December 23rd. Just look towards the bowl of the Little Dipper, and you might see about 10 meteors an hour. And now, with the rest of the December night skies, we're joined by Jonathan Nally, the editor of Australian Sky and Telescope magazine.
Good day, Stuart. Well, it's summer where I live, midsummer, and I love this time of year. In fact, I've just written an editorial for the magazine about one of the things I like about this time of year in terms of stargazing, and that is what we call open star clusters. Star clusters come in two sort of varieties. You have globular star clusters, which are like these massive cities of stars in space, but they're all formed into a ball shape or globe, a globular star cluster. And then you get what's called open star clusters, which are a sort of random assortment of stars. Generally, they all form together at the same time out of the one big gas dust cloud, but they're not in any sort of pattern, that they haven't contracted themselves into a ball shape or anything like that. They're just sort of random. And what I wrote in my editorial is that if you're looking with binoculars or just a small telescope, say, then globular star clusters pretty much all look the same, but with open star clusters, everyone's different. They've all got different shapes, different numbers of stars. They have, sometimes they have stars that are all pretty much the same color. Then you've got other ones that have stars of multiple different colors. And some of these clusters have nebulosity involved with them as well, and some of them don't. So there's an endless variety of them. And there are lots of really good ones to see at this time of year in some of the, particularly some of the zodiacal constellations, which are the ones through the Milky Way. There are ones in Gemini and Taurus. I'll get into them in a second, but it's a really good time of year to see these. And all you need for a lot of these star clusters, these open star clusters, is a pair of binoculars. So you don't need a super-duper telescope or anything expensive like that, just a pair of binoculars, and you can have a really good time sweeping through the Milky Way and seeing what's there and just coming across these star clusters one by one. So anyway, that's what I like about summer. And the other thing that we both like about summer is the constellation Orion, the Hunter, which is up right now for us in the southern hemisphere. It's to the north. For people in the northern hemisphere, it's down towards the south. It's brilliant with its big bright stars and stars in a row and everything. And of course, the famous Orion Nebula, which you can just make out with the naked eye if you've got nice dark skies and you'd let your eyes get dark adapted. But even then, you put a pair of binoculars onto it or a small telescope and you can see even more. So that's really good. Just to the west of Orion, you'll see a reddish star and then a triangle or wedge of stars. The reddish star is called Aldebaran, and the triangle of stars is one of these open star clusters. It's called the Hyades. It's really lovely. These are only loosely gravitationally bound to each other, these stars, and it's pretty close in space terms to Earth. It's only about 150 light years away. Don't need anything to see it other than your eyes. Just make sure you've got fairly dark skies. Don't stand under a street light or anything like that. Let your eyes get dark adapted, and you can't miss it. Just look for this sort of wedge, triangle of stars near a bright red star, and that'll be the Hyades. And nearby is another open star cluster, probably the best one in the sky. It's called the Pleiades, or the Seven Sisters. We've spoken about this one many times in the program. And it's called the Seven Sisters because it's said that most people, average eyesight, you can see 7 of the stars. People with better eyesight can see 8 or 9 or 10. I think people have seen 11 or 12, they claim, and I can believe it if you've got good eyesight. But in fact, the star cluster has about 1,000 stars. Most of them are too faint to be seen by just your naked eye or even a pair of binoculars. You need a telescope to see most of them. But get some binoculars onto the Pleiades, and it's really pretty. It's just really beautiful. These bright they look like jewels. They really do look like jewels. These bright, sparkly, bluish-white stars. It's just really, really lovely to see. Those are up in the northern part of the sky for us in the southern hemisphere, or the southern part of the sky for people in the northern hemisphere. For us, down in the southern part of the planet, way down south, down in the far southern skies, this time of the year, the Southern Cross, you can find it upside down if you go out in the evening. Depending on your latitude, it's either right on the horizon for someone from, say, the latitude of Sydney, or it's above the horizon for those at more southerly latitudes like Melbourne or Cape Town or something like that. Further north in Sydney, then, the cross is going to be below the horizon in the evening hours, but later on at night it will have risen as the Earth has turned, and so after midnight you'll be able to see it quite easily. If you have some good dark skies, you should also be able to make out the 2 nearest sizable galaxies to our own. And again, we've spoken to these on the program many times, but they're really worth seeing. There's the large and the small Magellanic Clouds. And they just look like faint, fuzzy clouds, but they are big galaxies. Smaller than our own Milky Way galaxy, but they're big galaxies. And you can see them nice and high directly south in the evening time at this time of year. So see if you can spot those. To the east of the large Magellanic Cloud is a really bright star called Canopus. And this is the second brightest star in the night sky. And further around to the east again is another bright star, a brighter one, and this is the brightest star you can see in the night sky. It's called Sirius, and it's known as the Dog Star because it's the brightest star in the constellation of Canis Major, or the Greater Dog, which is what that name means. It's interesting to compare these 2 stars too. So Sirius seems much brighter than Canopus, but that's because it's closer. In fact, it's just a little under 9 light years away. Canopus is 310 light years away, which is why it seems dimmer, but it's actually intrinsically a much brighter star. It's 8 times more massive than the Sun, Canopus, but Sirius is only twice the mass of the Sun.
And of course, Sirius won't remain the brightest star in the sky for very long. In 200,000 years or something, it'll move away from our solar system, and once again, Canopus will return to its rightful place as the brightest star in the sky.
I love Canopus. Yeah, I've got a real fond spot for Canopus. Most of the, like what they call the brightest, like the 20 brightest stars, most of the 20 brightest stars are south of the celestial equator. So we're quite spoiled down here in the south to see lots of these bright stars. Sirius is nice, but it's just, for some reason or other, I just love Canopus in the far southern skies. I think it's because of the constellations that are around it. There are some fabulous constellations down in the deep southern sky that we're so lucky to be able to see, particularly through the area of the Milky Way and the Southern Cross and Carina and Vela and all those sorts of ones. We're really, really spoiled. So Sirius, yeah, it's good. It's the brightest star at the moment. As you say, it won't always be, but I just got a soft spot for Canopus for some reason or other. So when you look up in the night sky and you see stars of different brightnesses, it's not always because the brighter ones are closer or the brighter ones are brighter. You can have bright ones that are further away and look dimmer, and you can have dimmer ones that are closer towards you and seem a bit brighter. So just need to look up a star catalogue or something like that and find out what's what. All right, well, let's take a look at the planets and see which ones we can see at the moment. Now, the biggest planetary event this month is what astronomers call the opposition to Mars, which is happening right now, even as we speak. Opposition, in space terms, is what we call it when a planet and the sun are in directly opposite directions in the sky, as seen from Earth. So as the sun is setting in the west, the planet is rising in the east. They're 180 degrees apart. And because the planet's rising as the sun is setting, that means you've got all night to view the planet, right, until dawn. So if you particularly want to spend a long time observing that planet, in this case Mars, then you've got all those hours in which to do it. Or it might be cloudy for the first half of the night and clear the second half, or vice versa. So it just gives you a lot of options in terms of viewing the planet. The other thing about opposition is that it very closely coincides with the point when the planet, in this case Mars, is at its closest to the Earth. And when a planet is closest, it looks bigger through a telescope. And this is particularly important when you're trying to view Mars, because Mars is actually a really small planet, and normally it's not too impressive when you see it through a telescope. So a few months from now, Mars will have moved further away from us, and looking through a telescope, you're not going to see much. So now's the time to do it. So at opposition time and closest approach time, the planet looks bigger, and with Mars, you can start to make out some details on the surface, such as polar ice caps, and sometimes even you get these huge dust storms that can completely envelop a planet. So that may happen this time. Fingers crossed it doesn't, because that ruins what you can see on Mars. So Mars is the big thing at the moment up in the night sky in terms of the planets. As for the other planets, we've got both Venus and Mercury, which are low above the western horizon after sunset. A little bit hard to see to start with, but as the month goes on, you can see them easier and easier. Venus is going to be rising higher and higher as the days go past. Saturn also is above the western horizon after sunset, but a bit higher up. And it's pretty easy to spot because it's fairly bright, is Saturn. Also bright is Jupiter, which is high in the northwestern sky at the moment, as seen from the southern hemisphere. If you have a look on December the 29th, if you can remember, go out and have a look on the 29th, and you'll see the moon and Jupiter very close together, only about a degree apart. The moon itself, the full moon, is about half a degree wide, so they're only going to be separated by about 1 degree, so about 2 moon diameters, which is pretty close. Of course, in reality, they're nowhere near each other out in space. It's just a line of sight effect as seen from Earth. And finally, this time of year, good old Earth reaches the December solstice on the 22nd. And the solstice is when the sun, or the December solstice is when the sun is the furthest south in the sky. That's due to our planet's axial tilt, and that's why it's summer in the southern half of the planet right now and winter in the north.
That's Jonathan Alley, the editor of Australian Sky and Telescope magazine. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.